Okay, in this episode we're going to look at chromatography. Chromatography is a technique that's used to separate out all the different components that make up a mixture, and it's a technique that's really important in environmental chemistry, and particularly around organic and biological chemistry. So in our science understanding, so the things we need to know about, it starts off talking about different forms of chromatography. I'll talk more about those in the next slide. It then talks about what are the key factors that allow us, I guess, to separate out the different components of a mixture. And that generally relates to whether they are polar or non-polar molecules. And hopefully you're familiar with polar and non-polar molecules at this point. So we'll go through some of that. And we're also going to learn about this idea of retardation factors, which is a basically way of quantifying, so turning something into a number to help identify the components of a mixture. So that's what we'll look at. So we're going to start with a few definitions. One word that we use a lot when we talk about chromatography is adsorption with a D. Adsorption is the attachment of particles onto a surface of a material, and it usually involves secondary bonds between the particles and the surface. And if you remember, secondary bonds are controlled by whether things are polar or non-polar, so that's why they're important. So this picture here shows what adsorption looks like. Lots of things stuck to the surface. It shouldn't be confused with absorption, which is the incorporation of particles into the body of a material. Like a sponge will absorb water, so the water goes into the sponge. This is not a term we should be using generally when we're discussing chromatography. So this picture just shows that comparison with absorption. Two very similar words, but an important difference in their meaning, and it's important that we understand that. A couple of other terms. When we talk about chromatography, we need to talk about the stationary phase. And this is the material onto which components of the mixture adsorb. So where we get the absorption. So like the example, I've got sort of an example over here that we did in the lab. That would be like the chromatography paper, was our stationary phase. The mobile phase is the liquid or gas in gas chromatography that moves across the stationary phase, carrying the mixture to be separated. So in the case of the experiment like we did in the lab, a bit like this here, that was the water or the methylated spirits. So this here just shows a little bit of a simplification of what we did in the lab. You put a dot on a paper, then you put that paper into the water, and as that waterfront moves up the paper, we see the separation out of all the various colours that were mixed together to make that black ink. So this is allowing us to separate out those different chemicals. In this case, these are all dyes that were all mixed together here at the bottom to make that black dot. So now we'll go to the next slide and talk about how that process happens. So as we go through this, I really do want you to keep this sort of picture in mind of what we did in the lab. And I know at the start it talked about a whole lot of different types of chromatography, and I'll come back to those, but the principles by which they all work are all the same. So if you understand this, you can apply it to a whole different range of different types of chromatography. So chromatography relies on secondary bonding, which is obviously dependent on the polarity of the molecule, which is, if you remember, polarity depends on whether things A have polar bonds, i.e. there's a difference in electronegativity between the two things making up the bond, and also whether they are non-symmetric, because if a molecule is symmetric, all of the polar bonds would cancel out, so overall it would be non-polar. If you need to revise that, talk to me or go back and look at the stuff last year from polarity. Polar molecules will bond strongly to other polar molecules, but not non-polar molecules. Non-polar molecules will bond strongly to other non-polar molecules, but not polar molecules. So this is the idea of why oil and water won't mix. Water is a polar solvent. Water and oil don't want to mix together. They don't want to dissolve in each other because one's polar, one's non-polar. Now, if we get to our chromatography, if the stationary phase is more polar than the mobile phase, polar components will bond more strongly to the stationary phase and move at a slower rate than more non-polar components. And the opposite applies. If the stationary phase is more non-polar than the mobile phase, the non-polar components will bond more strongly to the stationary phase and will move at a slower rate than the more polar components. So if we look at the experiment that we did in the lab, let's assume water here is our mobile phase, and that is a polar solvent. So we'll regard that as the, if you like, more polar part. And that means that our paper strip here is our stationary phase. Sorry for the messy writing. And we're going to regard that as the less polar. The paper is less polar than the water. And you don't need to be able to work that out. The question will always tell you that. So what that's telling us here is it's a bit like the bottom case. If the stationary phase is more non-polar than the mobile phase, non-polar components will bond more strongly to the stationary phase and move at a slower rate than the more polar components. So we could expect that the yellow here is more non-polar because it's stuck more to the stationary paper, which is also less polar. So less polar, or I could have said there, more non-polar, I guess. However, the blue dot up here is probably the most polar phase because that's actually wanted to stay with the water, which is the more polar component of this. The mobile component is more polar than the stationary, so that the blue dot would be more polar. So maybe we could mark that here. That's basically saying here we would expect that that one there would be more polar. So it interacted less with the non-polar stationary phase and more with the mobile phase and kept moving faster. And the yellow dot down here would be less polar because it interacted more strongly with the stationary phase, therefore it didn't move as quickly with the water. So how do we quantify this? And this is what this diagram here looks at. And we're looking at how far a dot has moved here. And we've got how far the dot's moved here. We've got how far the solvent front's moved. We measure those distances, divide them by each other, and we get what is called the retardation factor. It's a cool sounding name. So for any given mobile stationary phase combination, the movement of any component, so that's part of the mixture, relative to the solvent front is a reproducible property that can be expressed as the retardation factor RF. And RF is equal to the distance moved by the compound, that distance, divided by the distance moved by the solvent front, that distance there. And there you go, there's an example of working out a retardation factor. So there are lots of different types of adsorption chromatography, but all work on this same principle that I've just talked about above. Understanding the principle is the most important part. You don't need to remember every type and all the detail of each type, but you just need to be familiar with them. So just to make sure you're familiar with them, just read the text to get an overview of the different types of chromatography. Don't feel you have to remember the fine details, just remember the process. So just so you're aware, some of the different types of chromatography are like the paper chromatography that we did in the lab, thin layer chromatography, which is very similar to paper chromatography, but you use like a tile that's got either a polar or a non-polar coating on it that acts much like the paper. We can also do gas chromatography, where we basically put a mixture of gases. So the mobile phase is gases, and that goes through a very long, thin column, and that is surrounded by a stationary phase, and that stationary phase can both either be a liquid or a solid. Don't really need to worry about the detail there. But once again, the same principles apply as above. And we can also have high performance liquid chromatography, which is where we put through again, a mobile phase goes through a column. We put liquid, the mobile phase is liquid, and it goes through a column, which basically has a solid either sort of surrounding it, or sometimes it's basically just this porous solid that it goes through. And some of the, based on the interactions, based on the polarity of the molecules in a mixture, they'll move through that at different rates. You can also get, I should have added here, you can also get column chromatography. Oops, wrong size. Let me just get rid of that. You can also get column chromatography, which is basically a bit like liquid chromatography, where you have like a column, like a burette that we used previously. And in fact, I've done column chromatography in a lab, and we just use a burette and we fill it up with some solid that acts as the stationary phase, and then we pour a mixture through it, and the different parts of the mixture will move faster and slower through that column based on their polarity of those molecules. Just in the same way as the different ink stains moved up the paper at a different speed. I think it talks about that in the book, and you'll see pictures of that in the book, so I won't try and draw a picture here now. Finally, the last part here talks about ion chromatography, which has a lot in common with what we've just talked about, but is slightly more complex, and I think this is better to cover after we've covered some stuff on equilibrium and ion exchange. We can cover up later in the year. So I'm not going to do ion chromatography at this point. We won't have any questions in the test on ion chromatography. We'll leave this and come back to that later in the year. That's chromatography. Thank you.